about FireSim first up. Thank you.
Awesome, thanks. Yeah, thanks to all the organizers for hosting this awesome event. I'm super excited to be here. I'm going to talk about FireSim. FireSim is our platform for doing fast FPGA-accelerated hardware simulation, originally just on the cloud, but now on premises too. So just to set some context, what is FireSim and where does it fit into the architect or chip designer's design flow? Well, normally when we're designing these sorts of systems, right, we start with some high-level simulation to sort of spec out our idea. Then we start writing RTL and we start writing software and we plug it into some ecosystem. And you'll hear about Chipyard, which is one example of those tomorrow. Then you'll co-design in software RTL simulation, right? This is using a tool like Verilator to run micro benchmarks on your design. And then ideally what you would do is co-design using some sort of FPGA platform, right? Traditionally this has been prototyping. We'd really like simulation. I'll talk about the distinction between those two in a second. But the idea here is that we're going to boot something like a full operating system on our design so we can get realistic performance measurements. And then, of course, if we have time and the ability, we like to tape out a chip. But at this point, we've lost a lot of the co-design opportunity. So FireSim is going to fill this void here, number 4. We're going to build an FPGA-accelerated simulator to let us do this kind of middle ground co-design before we get a real chip back. So what is FPGA simulation? Well, to explain that, I'll take a step back and define what I mean by FPGA prototyping. So what happens if we try to use an FPGA prototype to model something like some SoC that we're going to tape out? So let's say this is a quad-core RISC-V system. We go and tape it out. It's going to run at something like a gigahertz. And if we have some DRAM attached to this thing, and let's say that DRAM has 100 nanoseconds of latency, right? Software running on this thing is going to see 100 cycles of DRAM latency. So of course, if we run performance measurements running software on this, we're going to get real results because it's a real system. But if we build an FPGA prototype of this thing, things kind of go south. So if we take that same RTL, drop it on an FPGA, it's going to run at something like 100 megahertz, right? But that FPGA is still attached to the same real-world DRAM with 100 nanoseconds of latency. So you can see the kind of performance mismatch here. And so if you run software on this thing, software is going to see 10 cycles of DRAM latency. And so this is incorrect by a factor of 10 as soon as you start using DRAM at all. And so this leads us to a couple of difficulties with FPGA prototypes. So in an FPGA prototype, there are a couple of problems. So first off, every FPGA clock is going to execute a cycle of the simulated target. And the performance of all of those FPGA attached resources, things like that DRAM or the SD card, all of that stuff is exposed into the world you're trying to simulate. And this leads to a couple of problems. So first off, we're going to get incorrect performance modeling whenever the FPGA resources aren't actually an accurate representation of your target system, especially when those performance ratios are changed because of the frequency differences. So for example, that DRAM performance being off by 10x on the previous slide. And your simulations are going to become non-deterministic, right? Like, for example, when you have a UART attached to this thing and a user typing in keys on the keyboard, you're immediately exposed to a real human, making it non-deterministic. And when you port across different FPGAs or different host systems, you're going to get different simulation results. So what we really want to build are hardware simulators that give us a couple of things. Of course, being as close to silicon performance as possible. We want it to be as detailed as silicon. And we want to have all the benefits of having software-based simulators. And I'll talk about what exactly I mean by that in a second. But think like sort of introspection capabilities. And we want it to be as low cost as possible. Of course, there are commercial platforms that do this that cost millions of dollars. That's not what we want. So our thesis here is that FPGAs are going to be the only viable basis technology for doing something like this. And so what we're going to do is build FPGA-accelerated simulators automatically using an open source tool, which is FireSim, that have this software-like flexibility built into them. So why can we do this now? Well, there have been a bunch of useful trends over the past couple of years in the architect, chip designer, kind of open source hardware person stack, right? So the first is having FPGAs in the cloud. And I'll talk about the sort of benefits of that a little bit later on. Then sort of as we're building towards getting something to simulate, to automatically transform designs easily, we need our designs to be written in some language that lets us operate programmatically on the RTL design. And Chisel and Fertile give us that. Then, of course, we need some hardware to simulate. Now, of course, looking at this conference, we see this huge proliferation of these open silicon-proven SoC implementations that implement an ISA that comes with lots of software. So, for example, in the academic research space, where we need to run substantial and interesting benchmarks, to get papers, for example, this is a stack that actually lets us build up real systems and get interesting results. So at a very high level, what is FireSim going to do? Well, it's going to produce these fast, automatic, and deterministic FPGA-accelerated simulators, so not prototypes, that we're going to use for pre-silicon verification and validation. So it's going to ingest a couple of things. So your RTL design in some form. To get all of the nice features, we have to ingest Fertile. That can come from Chisel, or it can come from one of the other ways you can generate Fertile. For example, some tools for taking Verilog and pushing them Fertile. Or it can just be black box Verilog, so we can handle various sorts of Verilog, but then we are sort of restricted to only having performance modeling and not some of the debugging and introspection capabilities I'll show you later on. And of course, we can ingest things like our own Chipyard frameworks generated designs. Then we'll tack on a bunch of hardware and software I/O models. We provide a lot of these built into FireSim, and you can write your own and bake them in too. So some examples we provide inside FireSim, things like UART, Ethernet, and DRAM. It'll also ingest a workload description, so how to map some workload that you've defined using a tool like FireMarshal, which you'll hear about tomorrow as part of the Chipyard talk. That lets you kind of concisely describe complex workloads like complete Linux stacks with dependencies installed and stuff like that, all managed automatically. And so in the end, it's going to produce that simulation I told you about, and we're going to do it automatically and deploy it onto either on-prem or cloud FPGAs, and it's very easy to move between the two depending on your use case. So the three distinguishing features here to sort of sum up this intro sequence is we're not building FPGA prototypes, we're building FPGA-accelerated simulators. And we're going to automatically do that from our RTL designs. And doing this is going to let us add a lot of nice debugging, resource optimization, and profiling capabilities into our simulator that we don't get with something like a prototype. Then we're going to have flexible scaling from on-prem to cloud FPGAs. We have a ton of standardization in here on AWS, as well as now sort of translating that to on-prem platforms. And there's this thing called the FireSim Manager, which automatically scales out simulations as necessary. And of course, all of this is open source, so that's why we're here. OK, so before we dive into some more technical details in FireSim, let's get some terminology straight. So we want to separate the target and the host machine. So the target, whenever I say target, I mean the machine we're trying to simulate. And the host is going to be the machine executing the simulation. So that RTL design that we want to go tape out, that's the target in our previous example. And we want a closed simulation world around it. The host machine, in our case, is going to be an FPGA fabric attached to some physical DRAM. But it could just as well be something like a multiprocessor. Right? So FireSim will generate FPGA-hosted simulators, just like a tool like Verilator will generate multiprocessor-hosted simulators. So FireSim is going to take your design and translate it into a simulator that runs on the FPGA fabric. All right, so how are we going to do this? The sort of key technique here is host decoupling. So we're going to transform the target design, so whatever RTL we wrote previously, into an FPGA simulator automatically. At a very high level, the easiest way to think of this is we just gate the design so we can control how it advances on the FPGA. Right? We're going to tack on models for various IOs. So for example, a DRAM timing model that will actually live on the FPGA fabric and present correct DRAM performance to the design. So then we're going to tie together your RTL design and all of these various models with this token queue mechanism that keeps everything synchronized depending on how you distribute it. Then we need to map this on the FPGA. So here's our FPGA fabric with some DRAM attached. We're going to allocate some resources to those host models. So that model I showed you on the previous slide is now living on the FPGA fabric here. And then we can drop down our transformed RTL design. So now if we run software on this RTL design, or just have some accelerator or something in this RTL design, it's going to see realistic DRAM latency, right? The requests coming out of this RTL design go through this queue and hit the timing model before they actually hit the physical DRAM attached to the FPGA. So the physical DRAM is still going to provide capacity, right? We need somewhere to store the data, but performance gets modeled by this timing model sitting on the FPGA. So what are the benefits of doing this? Well, we get a couple of nice things. So first off, our simulations are going to become deterministic because we're building a closed world around your RTL design. We get identical results as we move between different hosts. I'll talk about something called meta simulations later on, which are software simulations of an entire transformed FireSim simulation, which means you can, in Verilator, run a FireSim simulation not on the FPGA, but in pure software that will produce identical results and just run more slowly than running on the FPGA. And when we have decoupling, we get a couple of nice things. I won't be able to touch on all of these in this talk, but there are a bunch of references to papers and stuff that you can take a look at later on. The first is software co-simulation. This is kind of prolific throughout FireSim. We use this for various sorts of things. The idea here is that we can have software models sitting on the host machine that talk to hardware models sitting on the FPGA. So things like the block device and then the network modeling that I'll show you later on take advantage of this functionality. We can simulate very large targets over distributed hosts, and this was essentially the original purpose of creating FireSim, and that was our ISCA paper, and I'll talk about this in a lot more detail in a second. we can add a bunch of non-invasive debugging and instrumentation things, right? So this ability to stop the world and control the advance of hardware on the FPGA means we can basically capture things at unlimited fidelity without perturbing the simulated system. And we can do resource optimization. So again, because we control how time advances on the FPGA, we can trade off time and FPGA capacity for several sorts of hardware structures. All right, so what can you actually do with FireSim? The obvious use case is just evaluating SoC designs, right? So kind of classical performance measurement is running spec on a bunch of FPGAs in parallel. Back when Rocket Chip first sort of came out, you had FPGA prototypes. You needed a bunch of FPGAs if you wanted to run something like this fast. Now with FireSim, we can easily run on a bunch of parallel FPGAs on the cloud and run all of SpecInt with full reference inputs in like a day. And of course, people have used this for all sorts of different design space exploration. It's very easy to do things like sweep parameters, ship out builds, and that kind of stuff. There's been work in a bunch of other different domains, things like security, so doing things like replicating Spectre attacks, evaluating enclaves, tons and tons of accelerator designs. There's probably 15, 20 of these at this point that have been published using FireSim. And there's a lot of debugging capabilities built into FireSim too. So unfortunately, again, I don't have time to go into many of the details here. You can check out the FireSim docs. This is sort of an index of all the debugging features that are available in FireSim. Each one of these goes to a different page about some debugging feature. But some of these include synthesizing asserts. So asserts don't just get thrown away. When you go through the FPGA flow, we tack on some extra hardware, and if an assert fires when your design is running on the FPGA, you find out about it. And you get this nice message, tells you what line of code the assert is coming from, and so on. Same thing with prints. If you have prints in your design, we can stream them off selectively, depending on your performance requirements and how much stuff you want to log. We can also do things like automatically insert ILAs, all sorts of other good stuff. And we've used this, for example, for fixing boom bugs that happen billions and billions or trillions of cycles into simulation that would have taken a really long time to encounter in software simulation. And as I alluded to earlier, we've taken the same ability to stop the world and use it for profiling. So we can capture basically unlimited fidelity profiling traces out of our designs and reconstruct things like flame graphs that you traditionally would collect using a tool like perf with a restricted fidelity, restricted sampling, using something like FirePerf. OK, so I will quickly talk about the original use case of FireSim, which was modeling a data center. So I came into grad school wanting to do data center research. And that's why we initially built this platform, was to do that sort of thing. And finally, I'm kind of doing that actual research now after we've gone through the process of building FireSim. But let's go back to that original use case. So what does it take to model a data center? So we need to model a couple of things. We need to model all of that hardware at scale and do it accurately. And we need to run substantial software stacks on top. So very conveniently, around the time I was starting to work on this, AWS released the F1 platform. And what you see on the right is an example of an F1 16x large instance on EC2 F1. Basically, it's a beefy Xeon attached to 8 FPGAs, 8 Xilinx ultra-scale FPGAs over PCIe. So it turns out we can very easily map data center designs onto here. We're going to use RTL and abstract software model co-simulation to do this. So what's going to happen is the server simulations we can derive from RTL for RISC-V SoCs. That's what's going to run on the FPGAs here. And then network simulations, where we have relatively less parallelism in things like our switch models, we can run as C++ models on our processors here. Of course, this is a simplification here. You can go on to do things like model the switches on the FPGA and so on. But this is what we started with at the time. So these switch models here are not only in charge of modeling the network, but they're also keeping all of these simulations globally synchronized. Right? So we end up with this large globally synchronized simulator of some number of nodes. So let's build up to that. So let's start with kind of one node in this data center system. It's going to look like this. It's a quad-core RISC-V rocket-based system. Of course, you can drop in Boom or whatever else you want. This is what we had reliably working at the time 5 years ago. But it's this quad-core RISC-V rocket-based system. The thing we added to build FireSim was this 200 gig Ethernet NIC written in Chisel. So this is real synthesizable NIC implementation that sits inside the SoC and is a 200 gig Ethernet NIC. Conveniently, this takes about a quarter of the FPGA on EC2 F1. And so what we really wanted, though, was not just RTL running on an FPGA. We want a simulator of RTL running on the FPGA. So now we have that RTL design, and what you see here is taking that and transforming it into a simulator. So we've tacked on that DRAM model I showed you earlier and models for other stuff like the network links. And so if we run this on FPGA, again, about a quarter of an FPGA, we can run this at 150 megahertz if we don't run a network simulation, and about 40 megahertz if we run a network simulation. And I'll talk about the distinction between that a little bit later on. But of course, we want to model a data center, so we'll just start scaling out now. First, we'll just fill up this FPGA. So I told you it takes about a quarter of the FPGA to model one of those systems, so we're going to drop down 3 more copies. So now we have this 4-node simulation. There'll be a C++ switch model sitting down here that I'll show you in a second. That's modeling the Ethernet network between these 4 nodes. So they can all communicate with one another. These nodes can all boot Linux, run the regular networking stack, and so on. So I told you then that the instance we're running on doesn't just have 1 FPGA, but actually 8 FPGAs. So we can kind of scale out again and fill up this whole machine. So we've basically just dropped down 7 more copies of what I just showed you on the previous slide to get this 32-node rack scale simulator. So each of these FPGAs is running 4 simulations. Each of them are modeling a link to this top of rack switch model. So this switch model that's sitting on the host instance here, just a regular Xeon, the switch model written in C++ is communicating with each of these 32 server simulations, keeping everything synchronized, and actually modeling the 200 gig Ethernet network between them. And we can run this at about 10 megahertz. Of course, this doesn't look like a data center. This is just a single rack. So let's keep going. Because we're running on the cloud, we can just drop down more F1 instances and scale out that way. So what we're doing here is taking that one instance I showed you, dropping down 7 more copies of it on 7 additional instances, and adding on a regular EC2 instance an aggregation switch model. So this aggregation switch model looks just like the model I showed you earlier that would be talking to server simulations over PCIe. But instead, its job is to talk to other switch simulations over the EC2 host network. So this aggregation switch is communicating with each top-of-rack switch on each of these F116X large instances, and again, keeping everything globally synchronized across all of these simulations of 256 server blades. We wanted to hit a magic number of 1,000, so we could drop this down 3 more times. So at this point, we're modeling 1,000 nodes on 256 FPGAs on EC2, and we can run this whole thing at 6.6 megahertz. So that's still fast enough to boot Linux. Each of those 1,000 nodes can communicate with one another over this network. We're modeling this 1,000-node system with this 3-level network hierarchy. And the key sort of result here was that we were able to harness what was essentially millions of dollars of FPGAs at the time. Maybe now it's hundreds of thousands of dollars of FPGAs. To model this system containing 1,000 nodes with a globally cycle-accurate network, tying them together. And we only had to pay $100 an hour to run this thing, right? So this is something that was totally out of reach of academia and open source. But we could do this because we had access to these cloud FPGAs and all of this infrastructure to scale out. So speaking of that infrastructure, this sort of turned into a project for just doing productive open source FPGA simulation, right? So if we could simulate that 1,000-node system, of course we can simulate a single node system. And so we ended up open sourcing this when our paper was published. And since then, it's basically become this easy button for doing fast FPGA-accelerated full system simulation. So it works just like I told you earlier. You plug in some RTL design. We have tools for automating lots of stuff, FPGA builds, running simulations, and so on. And it scales to many different use cases. And the way we've hidden all of this complexity from the user is basically behind this command line program called FireSim. If you've used Docker or Vagrant or something like that, it's basically like that, but instead of containers and VMs being managed, it's FPGA simulations being managed. So as a user, you work on this regular compute instance in the bottom left of this image on EC2 F1. You run the FireSim command, and things like build farms that run long-running Vivado jobs or run farms that run simulations automatically get spawned and terminated in the background based on how you've configured the system. And another nice thing here is that because we have this automation, scripts can now call this program to completely automate the process of doing distributed FPGA simulations. So back in 2018 at ISCA, when we published this paper and released FireSim, we had a script in there before conferences had things like artifact evaluation. You ran that one script, and it reproduced all the results in the paper. And actually, for a while, this was basically kind of the final release check before we shipped a FireSim release. We just ran this script and reproduced all the results in the paper. Since then, conferences have introduced things like artifact evaluation, where reviewers go and actually try to run your thing and reproduce all the results. And at this point, FireSim has been used in a bunch of different papers, both at Berkeley and outside of Berkeley, to go through this artifact evaluation process where people who maybe have never even used FireSim, don't know about Chisel, don't know about Chipyard, can go reproduce paper results very easily. There's a bunch of documentation on the website, and AWS also gives grants for researchers if you want cloud access, and of course Xilinx donates to researchers if you want local FPGAs. There's been a bunch of community growth since then, a bunch of specs here, lots of projects with public FireSim support, and several companies also using FireSim. So Sci5 published a validation paper a few years ago at VLSI, validating their shipping chips versus a software model of their chips. And an interesting use case I'll talk about in a second is Galois deploying FireSim in DARPA FETT. So what is DARPA FETT? Well, to understand that, we have to take a step back and look at a program called DARPA SIF. So DARPA SIF was basically a program designed to have performers build hardware, or RISC-V processors specifically, augmented with security mechanisms that let you address common software vulnerabilities. The idea is that software is going to be vulnerable anyway. Can we make the hardware prevent those vulnerabilities from being exploited? And so performers built a bunch of stuff, and then DARPA made a follow-up program called FETT. And the idea was, let's assess how good those defenses in FETT were. And so they basically built this program where a bunch of remote attackers employed by a company called Synac would actually attack these designs running on the cloud. And many of these designs were hosted for attack on the cloud by FireSim. And so one example of this was Morpheus, a project from UT Austin, Michigan, and Jita Labs. And it was hosted on FireSim for FETT. And over 500 attackers tried to break this design, again, simulated in FireSim, working for really large bug bounties, think like 50K. And none of them succeeded. Of course, that's a testament to this design. But FireSim was there behind the scenes running all of these simulations. And this is a cool diagram from a workshop we held a couple of days ago of FireSim users. This is from Joe Caneri from Galois, talking about how they built the FETT infrastructure to run these FireSim simulations sort of transparently to the software security attackers. And there's a whole talk about this you can find on YouTube. FireSim has been used in a bunch of papers. There's a bunch more listed on the FireSim website. And FireSim users have also won a bunch of awards. I think at this point, FireSim has been used in published work from authors at over 20 different institutions. And this is really used, not just the paper was cited. A cool thing we've added recently is support for on-premises FPGAs. So we took all of that high level of automation we had for deploying on the cloud and made it so that it also supports local FPGAs. So you can use the same sorts of commands, configurations, to very easily switch from running on big, massive cloud simulations to a small number of local simulations or vice versa. So kind of the common use case we envision people going through is, you have one FPGA under your desk and a desktop. You do a lot of your development that way, but then you have a deadline. You need to ship a product or write a paper. And you can scale out very easily onto hundreds of cloud FPGAs when you're sort of under that time pressure. And you can use all of these existing FireSim features both at scale and locally, and it's very easy to move back and forth. If you're interested in getting started with FireSim, we've been running tons of tutorials. Here's our tutorial a few days ago at ASPLOS. These are basically full-day hands-on introductions to both FireSim and Chipyard, where we give you an EC2 instance on F1. You can log in, try all of the stuff, really run on FPGAs on the cloud, and so on. The slides are already available here on this website, and we'll be posting the videos probably tomorrow. And we'll be hosting another one of these at ISCA in Orlando in June. If you're also interested in learning more about FireSim use cases, including that Galois DARPA FETT use case I talked about earlier, videos from our workshop also at ASPLOS a few days ago are also available online at the link here. If you just go to fires.im, you'll find your way to all of these pages. With that, I'll wrap up, and I'm happy to take any questions. Thanks.
Thanks, Sagar. If I may ask the first question, I'll break the ice. So it seems like every time we hear a FireSim presentation, there's more and more impressive stuff being kind of bundled with it. Like, what do you foresee the future of the project, as perhaps, this post-grad group graduates or moves on or whatever? Like, do you see industry people picking it up or continuing to kind of spread throughout academia? What do you think the true development will be driven by in the coming years? Yeah, that's a very interesting question. I think we're sort of at a critical juncture in the FireSim project where we're also trying to answer those same questions. So I don't have like a solid answer for you. There's
industry adoption, places like Sci5 are using it pretty heavily and contributing back. There's a bunch of academic users in different places also contributing back. I think we're not super solid on the governance structure that we want going forward. So I think that would be an interesting discussion topic I'd like to chat with other people here too.
Cool. All right. Sounds good. Philip has a question.
Thanks for the presentation. So I have a question about kind of checkpoint and restore for the simulation. So can you kind of stop them at some point, checkpoint them, and restore them from that? And can you restore them only on FPGA, or can you potentially restore them on a software simulation as well?
That's a great question. We don't have that feature right now. So people have been thinking about this in various forms. The sort of just capture the architectural state one is generally easier. Some folks have done that. There was a presentation at the workshop where people did that for a particular design. They only captured architectural state, restored it in a software simulator, and then let it run for a little bit of time to kind of reproduce the entire state of the system as closely as possible, and then run forward. I think the capture everything sort of flow is something that we would like, but is also kind of difficult to totally figure out with respect to mapping between the RTL design and what's on the FPGA. So it's definitely an interesting area. I think it'd be great for someone to work on. We haven't had the power to do it yet. Yeah.
I might have missed this in the talk, but does your design have to be in Chisel, or can it be in another RTL language?
Yeah, so great question. So there's sort of two avenues here. So if you want all of the sort of nice debugging and profiling features, it has to be in Fertile. Where that comes from is up to you. It can be Chisel, it can be some other compiler that generates Fertile. If you just want the performance modeling capabilities, then it can be System Verilog or something else. We can black box it in a wrapper at the top level and just simulate anything. And it just gets clock gated and we can model performance correctly.
If you're relying on clock gating for the simulation, what about designs with multiple clock domains within them?
Yeah, so that's why the actual transform is a little more complicated. So if you do something like that, so FireSim will handle clock gating as it's expressed in Chisel. So if you have a design that is not Chisel that you want to, that has multiple clock domains, you need to kind of decompose it at the top level and then map out your multiple clock domains in Chisel and drop them in. If you have just a Chisel design with multiple clock domains, that's no problem.
Okay. Thanks, Sagar. Thank you very much. Cheers.